Okay, so this is section 6.8, which is titled Exponential Growth and Decay. And we're going to start off by looking at a model, A of t equals A naught, or A sub 0, times e to the kt. So basically, we're looking at this to model like population growth or the rate at which something decays. And then we're going to look at a couple of examples of kind of applications that you'll be asked to take a look at. So first, let me kind of explain this model, this function for you. All right, so A of t, so that's the amount after the growth or the decay occurs. So that's A. A sub 0, or A naught, is your initial amount or initial size of a population, and then it grows, where A would give you, again, the size of the population after the growth. Or if you had a substance that was decaying, A sub 0 is the initial amount of the substance, A is the amount that's left after the decay has occurred. So now E is the number. Remember, E is the number exponential E, which is what, about 2.71. But you'll use, when you find approximate values, you'll use the E button on your calculator. K is the constant. Now when K is positive, that is in a growth situation. And when K is negative, that is a decay situation. And then T is time. So, for example, you might see something like this, where it says, okay, the size P of a certain insect population at time T in days obeys the model P of T is equal to 500 times E to the 0.02 T. And you might ask to answer a series of questions like these. So let's look at the first one. Okay. Letter A says determine the number of insects at T equals 0 days. Alright, so I would sub 0 in for T. So P of T, or P of 0 in this case, is equal to 500 times E to the 0.02, and then I sub 0 in for T. So when I evaluate this, this will give me the size of the population when, on the 0 day, on the initial amount. This should give us the initial amount. So 500 times E to the 0.02 times 0 is 0. E to the 0, any number to the 0 power is 1, so this is just equal to 500. Again, which makes perfect sense, because remember, in our original model, we would have P of T is equal to, this would be P sub 0, which would be your initial amount, times E, the 0.02 is the constant, and then we subbed 0 in for T. So when T equals 0, meaning at the very beginning, the population is 500. So for letter B, it says, what is the growth rate? So the growth rate is K. So since K is equal to 0.02, the growth rate we're going to look at as a percent. So 0.02 as a percent would be, you would move the decimal point over 2 places, would be 2%. So the growth rate is 2%. Now letter C, graph the function with a graphing utility. Alright, so we're going to take a look at this function. You can just pull up fooplot, or you can use a graphing calculator. So I decided to just use fooplot, and in doing so, I couldn't get it to accept the e as a number, so I just subbed in 2.71. So I entered 500 times 2.71, and then in a caret, and then in parentheses, I put 0.02 times x. I didn't use t because I think fooplot looks at functions in terms of x. So I did have to zoom out a little bit. If you want to see the exact window that I ended up using, my x window, I went from negative 100 to positive 100. And my y window is from about 1,000, negative 1,000 to positive 1,000. So you can see the nice exponential function. Again, this is looking at population growth, so we're looking at an increasing function. Alright, so let's pull this back up. Okay, so what is the population after 10 days? Okay, so what is the population? So what is the population size? Again, we're looking for P again. So P is equal to 500 times e to the 0.02, this time after 10 days, so I sub 10 in for t. And then again, you're going to go to your calculator to find a value for this. Now, everybody's calculator works slightly different, so it's important that you know how to use your calculator. If you're using a regular graphing calculator, you're basically going to just type in exactly what you're looking at. Most calculators work that way now. However, I was just pulling up the computer calculator, and this one works kind of like the old-fashioned ones. In order to plug this into this calculator, I have to do the exponent first. So I'll go, okay, 0.02 times 10. I could have said that was just 0.2, but we'll go ahead and do it. And then I need to access e to the x. So in this case, it's the inverse. I have to hit the inverse function for that to pop up, since e to the x is the inverse of natural log. So then I hit e to the x. So this value is e to the 0.2. And then I'll multiply that by 500. And that gives me approximately 610, was it? 610.70. So just pay attention on MyLabs Plus to see, what you need to estimate or approximate to. So again, to answer the question, after 10 days, the population, this insect population, would have grown from 500 to 610. All right, let's take a look at letter D. Oh, that was letter D. We didn't do anything for C. That was just the graph. So we're on letter E. Okay, when will the insect population reach 800? So this is saying when. So I'm looking for T in this case. So find T when, I'm going to say when P is equal to 800. So I want to know how long it will take for the population to go from 500 to 800. So I'll put 800 is equal to 500 times e to the k is 0.02, and in this case t is what I'm looking for. And again, going back to just that general, how this model works, remember 500 is the initial, 800 is after the growth. K is the constant which is given, and in this case I'm looking for t to see how long it takes for that growth to occur. So now you got to think back on how to solve this kind of equation. So I want to get the exponential expression by itself. So I'm going to divide both sides by 500. So this is 800 over 500 is equal to e to the 0.02t. Alright, so I can just think of that as 8 over 5. But to bring that t down to a place where I can solve for it, I need to take natural log of both sides. So natural log of 8/5 is equal to the natural log of e to the 0.02t. And now I can bring this exponent down in front. So this is natural log of 8/5 is equal to 0.02t times the natural log of e. The natural log of e is 1. So 0.02t times 1 is just 0.02t. So to get t by itself, I divide both sides by 0.02. So t is equal to the natural log of 8 over 5 divided by 0.02. Okay, so now to enter this into your calculator to get an approximate value, again, it kind of depends on your calculator. What you need to be careful of is you need to make sure you're telling your calculator to find the natural log of 8 divided by 5, and be careful because it's not the natural log of 8, that value divided by 5. It's the natural log of 8 divided by 5. So you want to make sure it's taking the natural log of that quotient and then dividing the natural log by 0.2. So again, you just have to be able to communicate that to your calculator, and it depends on what kind of calculator you're using. Alright, I'm just going to use this one that's on the computer. So I have to do 8 divided by 5 and find that value. Then I hit natural log. If you're using a graphing calculator or a more updated calculator, you'll be able to enter natural log and then in parentheses 8/5. Again, you just have to play around with the calculator that you're going to use on the exam to see how it works. So that's the natural log of 1.6. I'm going to divide that value by 0.02 equals, and that gives me t is approximately 23 point, what was that? 23.50. And that was in days. And you should ask yourself, does that make sense? So again, this was, okay, the insect population would go from 500 to 800 in 23 days. Yeah, that seems reasonable. Okay, so then letter F. When will the insect population double? Alright, you'll see some other questions like this where you're looking at how long it takes something to double or triple. You saw this in the compound interest problems too. So again, our original model here is P of t is equal to P sub 0 times e to the 0.02 t. So if I want to know how long, again, I'm looking for a value for t, and I want to know how long it will take for the population to double. There's a million different ways you can actually go through this. You can enter a number, okay, 500 is what we started with. If it doubled, it would be 1,000. So I can set this up to see how long will it take for the population to go from 500 to 1,000. But it doesn't really matter what the initial amount is. You just want to know what double that is. So if the initial amount was 1, doubling that would be 2. It's going to work the same way every time. So I can just say, okay, the initial amount is just P, and the double is 2 times P sub 0. And see what happens is the P sub 0 cancels every time. So I'm really just looking at 2 is equal to E times 0.02 T. I'll take natural log of both sides to solve this. I'll bring the exponent down. Natural log of e is 1, so t is equal to the natural log of 2 over 0.02. And again, I can plug that into a calculator to get an approximate amount, which will be, let's clear this, so 2 natural log divided by 0.02 is 34.66. And again, that was days. And again, does that make sense? So for the population to double, to go from 500 to 1,000 or 600 to 1,200, it would take a little over 34 days. So yeah, that makes sense. Alright, so that takes you through some of the basics of growth and decay. Again, this one we looked at the growth of something. Decay would work very similarly. It would just, again, you'd be starting with an initial population, and instead of getting bigger, it would be getting smaller. So take a look at these questions on MyLabs Plus, and always feel free to ask if you have any questions.